Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 7-1 lesson on graphing conic sections. In this one, we will be graphing specifically circles, semicircles, ellipses, and hyperbolas. Now, some of you might be wondering what cones could possibly have to do with two-dimensional shapes. So if we take a double-napped cone, which is this kind of deal here, and cut it into pieces, we can form four shapes. One shape, as you see here, is a parabola. Another shape, if you cut this horizontally, is a circle, or if you cut it at an angle like this, but still kind of going across the whole cone, we've got an ellipse. And finally, if you cut it up down like this, we've got a shape called a hyperbola. So these are the four shapes we'll be focusing on in this lesson, but really, if we're being honest, mostly circles, ellipses, and hyperbolas. We're going to begin this lesson with the simplest of these shapes, a circle. So here's the equation of a circle. How do we know that? Well, I told you, graph the circle. But another way you could figure this out is knowing the general circle formula, which is x minus h squared plus y minus k squared equals r squared. So basically, you have an x squared, a y squared, and some other number, and you're adding these things together. So in this case, how do we graph one of these? Well, you may have graphed circles before, so if you have actually, pause the video and see if you can remember how to graph one of these. Okay, let's see how that went. Now, if you didn't graph circles before, just follow along. First thing we need to do is find the center and the radius of the circle, the two most important parts. We need to know the center of the circle, and we need to know how far to go in each direction from that center. The center in general is going to be h, k. So whatever is being subtracted from x, that's the x value of your center. Whatever is being subtracted from y, that's the y value of your center. And it actually works that way for all of the different conic sections we're going to be doing today. So this is a recurring feature here. In this case now, our center is going to be -2, 1. Plus 2 means we're actually subtracting -2 inside this squared parentheses. So -2, 1. Next, I need to find the radius. Now this is where it helps to know that general circle formula. The number on the right side of the equation here is an r squared, so that means this 9 is really r squared, which means r itself must be the square root of 9, or 3. Now that we've got the center and the radius, we're going to plot the center, so that's going to be -2, 1 right there. And now we are going to use the radius to draw 4 dots to the left, the right, up, and down from the center. The radius tells you how far you're going in each direction, but really the only 4 directions you can be sure of are left, right, up, and down. So I'm going to start at the top here. We're going to go up 3 here, and then I'm just going to work my way around clockwise. So we go right 3, down 3, and left 3. And again, I can't really go diagonally because grid lines, this isn't exactly a distance of 3 here. This is actually going to be more than 3 in this direction. All right, now we just have to connect the dots. Or, in other words, draw the circle. So here we go, the magic of animation, and there is our circle. The next thing we're going to graph is actually going to be a semicircle. While this is not a true conic section, it doesn't really belong anywhere else, and we just graph circles, so why not, right? So now we see a single variable that's not being squared equaling the square root of some constant minus a squared variable. There's a pretty good chance you're doing a semicircle. So to start this one off, we're going to square both sides of this thing and actually turn it into something that looks like a circle. So on the left side, I've got y squared. On the right side, I've got whatever was inside this square root, 25 minus x plus 2 quantity squared. Note that this negative out in front is going to go away because I'm multiplying a negative by itself. All right, so now we're just going to move the x plus 2 squared over to the left side. And voila, we have the equation of a circle. We're now going to graph this circle, sort of. So what we do if we were going to graph a circle is find the center and the radius. So we're still going to do that, keeping in mind that this is kind of a fake radius because we're not going to go that distance in every direction because it's a semicircle. So now our center, that's going to be -2, there's nothing inside this parentheses. That means we have a 0 for the y value of the center. So -2, 0. Radius is just going to be the square root of 25 over here, just like a regular circle. So that's going to give us 5. And at this point, we have to figure out which half of the circle we're graphing. So we're going to figure that out by using the format of the original equation up here. That'll tell us which half of the circle we're drawing, and we're going to use 3 points when we draw this out. But let's figure out which half first. So I made a little table here. There's actually 4 different possibilities you can have. So on the left side of the equation, you could have an x equals or a y equals. And on the right side of these equations, you're always going to have either a negative square root or a positive square root. And depending on which combination of variable and sign you have, that tells you which half of the circle to draw. So for example, if you have an x equals negative square root, that means you have a left-right semicircle, and since it's negative, you're going to draw the left half of the circle. What do you think you're drawing over here for positive square root? Oh yeah, the right half of the circle. Pause the video and see if you can figure out what y equals negative versus positive means. Alright, so if you have y equals negative square root, we are doing the bottom of the circle. Positive square root, we're doing the top of the circle. Now, in this case, if we look up here, and I've highlighted this in red for us, we have y equals a negative square root. So based off of our chart here, that means we have an up-down semicircle, and it's going to be on the downside. It's going to be the bottom half of the circle because we've got a negative here. Now, before we actually graph anything, I also want to make sure we have the scale right on this. And I didn't worry about that on the last graph, but we've moved on to bigger and better things. So let's start thinking about the scale. I have a center of -2, 0. So if I just leave this scale the way it is, that's going to be right here. Now my radius is telling me I need to go 5 in every direction. So I'd have to go 5 this way, 5 this way, 5 this way, and you'll notice that's going to take me off the graph. So to make things a little nicer for myself here, I'm actually going to make my grid lines go by 2s on this one, and you really have to know the center and the radius in order to anticipate this and fix it before you start graphing. Alright, now that we've got that done, we have our center. That's going to be -2, 0, which is now right here because our grid lines are going by 2. And now I have the bottom half of the circle I'm graphing. So I have to go 5 this way, 5 down, and 5 to the right. Yep, that's 5. And that'll give me the bottom half if I connect those dots. There we go. For this next example, it kind of looks like we're graphing another circle, but things are a little different here. This, in fact, is the eccentric cousin of the circle, the ellipse. So my general ellipse formula here is kind of like a circle formula. We've got an x minus h squared, just like a circle, also a y minus k squared, and we're still adding things. However, you'll notice that we don't have an r squared on the right side of the equation. This 1 that you see here is actually built into the ellipse formula. And instead of an r squared on the right side, we have these 2 r squareds in the denominators. I call them rx and ry squared. Now, in most textbooks, these are a squared and b squared, but I chose to rename them like this just so it's a little more clear what they are. We'll talk about what they are in just a sec. So to graph one of these, how do we do it? We're going to start, just like a circle, by getting the center. And I'm going to hold off on plotting it until I see what my scale is, but I can at least find the coordinates of the center. In this case, that's going to be -2, 0, because this is y minus 0 squared up here. And now, what are these r's down here? Well, this rx, I called it rx because this value down here is the square of the horizontal radius, or the x radius of this ellipse. An ellipse looks like a circle, only it has a different left, right, and up-down distance from the center. So my next thing I'm going to do is find this rx value, this x radius, and I do it just like I did when I was finding the radius of a circle by square rooting a number. In this case, I'm square rooting whatever is below the x squared, which is the square root of 4 here. So that gives me a left-right radius of 2. Next, I'm going to find the ry value here, the y radius. That's going to be the square root of whatever is under y squared. So that's going to be the square root of 9, which is 3. And now I have everything I need to graph this ellipse. So I'm going to draw my ellipse using rx for my left-right points and ry for my up-down points. We'll start at the center. We've got -2, 0, and now I'm going left 2 and right 2, and my ry value is 3, so I'm going up 3 and down 3. And just like before, connect the dots. And there we have it. Here's another ellipse for you to draw. Pause the video and see if you can get accurate on this one. All right, let's see how that worked out. So we start with our center, which is going to be 0, comma 1 in this case. For my Rx, I've got the square root of 16, which is going to be 4. For my Ry, I have the square root of 9, which is going to be 3. And just kind of thinking ahead about what I'm doing here, I've got 0, comma 1 as my center. I need to go up and down 3 and left and right 4, so I can keep a scale of 1 on this graph and still be able to graph all this. So there's my center. We're going left 4 and right 4, up 3, down 3, and draw the ellipse. For this next example, this equation kind of looks like an ellipse with one key difference. We have subtraction instead of addition here. So this will actually give us a hyperbola if we sketch this. There are two different hyperbola formulas. One has an x squared minus a y squared in it, and we still have the rx and the ry squared on the bottom, just like an ellipse. We have a different left, right, and up-down dimension to this thing. Another way you could see these, though, is you might see a y squared minus an x squared. And then the up-down radius and the left-right radius go with their respective variables. So how do we graph one of these? We're going to start by graphing it kind of like an ellipse. So we'll start by finding and plotting the center and the two radii there. So we have a center of, we'll actually pause the video and see if you can find all that stuff. All right, so we have a center of 0, 0. Couldn't be easier on this one. Now for the left-right radius, the Rx, that's the square root of 4, which is 2 in this case. And for Ry, we've got the square root of 9, which is 3. So we're going to go ahead and graph all this right now. We've got 0, 0. We've got left 2 and right 2. And up 3 and down 3. It's not always 3, I promise, on the up-down, but it's worked out that way so far on these examples. Now here's where it's a little bit different than drawing an ellipse. Instead of drawing an ellipse, we're going to draw a dashed box using these as kind of the midpoints of each of the sides, like so. So there's this dashed box. Now we're also going to draw some asymptotes. We're going to draw an asymptote through each corner of this box. So we have an asymptote going from bottom left to top right, and we have another asymptote going from here down to this direction. So these asymptotes are going to be guidelines for when we actually draw the hyperbola. We haven't actually drawn anything that's part of the hyperbola graph just yet, but we're getting there. So the next thing we're going to do is we're going to use the variable that's in the positive fraction of the equation here to decide if this hyperbola is a left-right hyperbola or an up-down hyperbola. Here we see that we have a positive x squared. That means that this is going to be a left-right hyperbola. We're going to have branches on the left side and the right side. Some hyperbolas have them on the top and the bottom, but not this one. So our next step is just going to be to draw the two branches, going through whatever point we drew on that side and also approaching the asymptotes. So we have a left branch over here, approaching our asymptote, going through this point and approaching the other asymptote, like so. And then we're going to draw another branch over here doing pretty much the same thing, but going to the right instead. And these two branches are the only things that are physically on the hyperbola. We're going to do one more example with a hyperbola. Pause the video and see if you can do this one on your own. All right, let's start with the center. Now be careful doing this because you'll notice that the y comes before the x here. So we've got an x value of 1 and a y value of 0 for my center. And now the rx on this is going to be the square root of whatever is under x squared. So square root of 4 is 2. For ry, that's under the y squared here. Square root of 9 is 3. So we actually have the same dimensions as the box on the last example, only the center is not 0 anymore, 0, 0. It's 1, 0 right here. So we're going left 2 and right 2. And, again, just check the scale to make sure you'll have enough room. But it looks like we'll have enough room to draw everything here. So we're going up 3, down 3, drawing the box just like before. Asymptotes through the corners of the box, just like before. Now this time around, the y fraction is positive. That means that we have an up-down hyperbola instead of a left-right one. So that means we're going to draw a branch up here at the top. and another branch down here at the bottom. So pretty much the same as the other example, only the center got moved and we had up-down instead of left-right. This concludes our lesson on circles, ellipses, and hyperbolas. Till next time, Mr. Sutton, signing off.